So this is going to be the last, actually, wait a minute. Are we missing anybody or everybody? Everybody seems to be here. Okay. So this is going to be my last presentation for this workshop. Obviously, I'll be around still for this afternoon exercise session. But well, so today I want to just wanted to talk about photonic crystals in ANSYS, like how to do transmission and reflection measurements. And before I just go back to this thing, I just want to like basically advertise what I want to do, huh? So I mean, this morning you saw how to do a photonic crystal. I mean, yesterday we did mechanic photonic crystal, and there we also had a same problem, huh? So we calculated the photonic crystals, the band gap, and then remember, guys, I need you everybody back then. Oh, hello. I need you to be sharp, because just please listen to me, and I mean everybody needs to be sharp. We have a little bit of time and then a lot of things to do. So the thing is, so back then we have this problem. We calculated the photonic crystal band gap, and we know the band gap assumes we have an infinite chain of like a infinite long chain of these unit cells, huh? But then the relevant question you might ask is like, how many unit cells are enough number of unit cells to stop a wave? Okay. So we have the same situation with photonic crystals. So if you calculate a band gap, you have a band gap. It means that if you have infinite number of unit cells, you can stop that certain, basically, like certain wave cannot propagate through this photonic crystal because it's a band gap. But you know that we cannot fabricate like basically infinitely large, infinite number of holes. So we need to know how many unit cells are good enough number of unit cells. And the motivation, I mean the real example that I want to focus today and optomechanics is this sort of couplers. I mean, if you don't know this work, please go and read it. This is one of the most famous works done by a group of Oscar Painter. We also have some similar ideas. And the idea is like you have this, photonic crystals, and people used to do like basically this photonic crystal that you saw in Leo's talk this morning, and people used to use this dimpled taper fiber to couple lighting, but that was really difficult because the vibration of this thing was an issue. So they started to investigate another method, which is this one. So you have a waveguide, and what you do at the end of this waveguide, you pattern a photonic crystal. It's different than this photonic crystal. There is no tapering in a sense that you change the pitch. And this is practically just a Bragg reflector. So if you have enough number of unit cells, it's like just a DBR mirror, but on a waveguide. So you have a periodic structure of like N1, N2, N1, N2. It's like a Bragg reflector. So everything that comes to this waveguide, it reflects off, and because of this evanescent field, a part of this wave couples to these modes, and that's it. And then today I want to just, so we saw the band gap diagram here, and today we want to basically simulate such a thing, and see launches wave from one side and see how does it reflect off and how much it transmits through and how much it reflects back, to see the efficiency of this waveguide as a function of number of unit cells. Okay, but since this is and just a motivation why we have done ANSYS, because if you do this sort of simulation in COMSOL is absolutely inefficient for doing this. So now you have seen some examples in COMSOL. COMSOL is a good eigenmode solver. It's a decent stationary solver, but absolutely it's not a good finite element solver. It's very slow in that sense. And I started obviously doing this at the beginning in COMSOL. It takes ages to converge, so I look for other solution like ANSYS. It turns out it's much more powerful, basically, software to do this job, But so basically, if I go back to my presentation, well, this is the thing that we want to simulate. So basically, reflection of this basically a finite number of holes, and we want to see how does it reflect. If this is a very good, absolutely good reflector, we should see like reflectivity 1 at the band gap, But then we will discuss that actually you need to have sufficient number of unit cells, but also have other stuff like this, this thing which is called basically impedance matching circuit, in order to reach this basically complete reflectivity. Well, and then I tell you that we go to COMSOL. Instead of COMSOL, we use ANSYS for this type of. I mean, this type of simulation is different than anything we have done before so far. I mean, what we have done so far was like Argand mode solver or stationary problems. Now the problem is different. So what I want to do, I want to launch a wave from this side. It goes in, it propagates. Some of it actually reflects off this surface. Some of it goes through. And I want to know how much of it goes through, how much of it comes back for different frequency. So this has excitation and ports. It's sort of a FEM simulation. And then I need to tell you this, before doing that, there are two ways to do this. You can do it in time domain. It's called FTDD. Or you can solve the equations of motion in Fourier domain, which is FEM. So that would be a single frequency. I think can you open the door? I think Tobias is behind the door. So somebody. Thanks. Yeah. So practically you need to, as I said, you need to have a yeah, so this is different than any other simulation we have done. So it's not Argand modes. We are not looking at Argand modes of this waveguide. We are not either interested in a stationary solution, but we want to launch wave from one side and then see how much of it comes off from the other ports, right? And then if you do it in FTDD, you can see the transients. You can see because so the FTDD you just basically look at the step basically response, or you launch a delta function and then see how does it propagate, and then take a Fourier transform. Or you can basically calculate the Maxwell equations in phasor domain. Fix the frequency and then calculate the time derivatives, simplify the time derivatives, and then just calculate the spatial derivation. Each one has its pros and the cons. Obviously, for single frequency, FEM is much faster than FTDD. But if you want to know a range, like a sweep, then FTDD might be also a good option, because then it's broadband, because it gives you a delta response, so you can take a Fourier transform. But also, as you saw, it has a relatively okay graphical user interface. It has a built-in adaptive mesh, which I'm going to just discuss right now. High power computation. You also saw that polar cluster computation, etc. So basically ANSYS is a good software. Well, so I had also, as my first example was really to how to make a basically forget about photonic crystal waveguide, launch wave from one side and then side from the other side. But since happens to be the first example of this, COMSOL ANSYS guy was the same thing, so I just skipped the first part of my talk, which is building this model. So I assume now you have a model, which is we just build the geometry together in the first before launch, and I just solve it for you and then show you how to extract data, how to see mesh, how to calculate S12. Okay. Okay, so guys, before I start, and I need everybody to be sharp because I have very little time. Is there anyone here that doesn't have the geometry with the proper excitation and proper boundary condition? That's all I need to have. Okay, two. Mohammed, can you help these two? You okay? So where are you guys? So many. No, forget about running it. Do you have the geometry plus excitation? This is all I need. I will redo it. Well, just can you help? Okay. Okay, guys, I would. So what we're doing at the first 45 minutes? Huh?
Can you, for instance, save this one and put it on the?
Yeah, that's actually a good point. So since you have seen how to draw it, I don't do the redrawing. I'm just going to save it, put it in the in this Google Drive, just download the same geometry and then we build on this. Huh? So to do that, actually just clean up the result. Oh, so there's no result. So just save this and desktop. Call it curved waveguide. Okay. And now if you go to slides, Amir Ghadimi, then you have this photonic crystal mirrors, and I just put this folder here. Did it do? Damn. I don't have edit privilege, I guess. It's a few kilobytes. I'm gonna email it to you. And then you put it there, Muhammad. Let me just send it to zip this. Shit, damn it. This is attachment. Okay, so just give it a second. So Muhammad will just put it in a. Did you put it in a hard drive? Google Drive. Yeah. Okay, guys. Now it's in a Google Drive. Please, everybody, can you download this geometry, and then we start from there. Now, if you go to the Google Drive, where did you put it?
Google Drive, slides, your slides, Photonic Crystal Mirror, and there's a bend waveguide.
There's not.
Just refresh it. Refresh.
Nothing.
Yeah, there is. Refresh again. Go back.
Damn. I will just open it in a different. As long as you see it, it's fine. I don't see it here. Shit.
Yeah, I can see it.
You can see it? Okay. Is there anybody without the geometry still?
Yes.
Who? Muhammad, I don't see it.
Yeah. I put it in the root also again. The root of 1.
I don't see. This is not logged in. So I'm refreshing it. Nothing's. I have it here, so it doesn't matter. Guys, everybody has it? You don't have it? Just who doesn't have it? Okay, Muhammad, can you just go to this guys, because I cannot like spend half an hour just to download the file. Please go to one by one.
Also in the main. Everywhere. Do you have the original book?
Everyone, you see it?
Yeah, yeah, I could see.
How can you see that can't see it here? I don't understand.
Yeah, I think yeah, because I remember you learned, but actually I didn't succeed. I mean, I followed the comment because I had like a problem. I couldn't do it.
What I have to do is actually.
What was this public link? You have it?
Can you try closing the Google Drive and entering again via the link?
Can somebody open the door? Ehsan, can you? You have it now? Muhammad, can you just raise your hand if you don't have it, please, because we are out of time. Leo, can you also join? See, Ehsan, can you also join? See, what's the problem? They cannot see the Google Drive. Okay, so fine. So everybody has it then. Okay, so just open the file. You should see the same thing that I'm seeing here, and then we're gonna continue from the geometry you built this morning. Okay, so everybody. Well, so what you have done this morning is just there. As you saw, there are different taste of making geometry. So this basically Marcus actually made the geometry while it's revolving. I told you normally it might be better to do it in 2D and extruding, and indeed that's most of the time what I do. It tends to be much easier than all this moving and so forth. So what do we have here? We have a geometry. If you come to this solid parts, you see we have a silicon part. Silicon, why it has silicon dioxide? Let's change the material to silicon nitride instead of silicon dioxide because it has much larger refractive index and it can confine light better than silicon oxide. Again, just to remind you, if you come here in solids, you should have silicon dioxide, and then inside you have an object. It's called waveguide. Let me activate this magnifier again as well. So if you come to this waveguide, it will basically highlight the waveguide. If you if you double click, you would see all these properties that it was hidden in this basically bottom left. If you double click on it, also does the same job. So let me go out of this magnifier. So now you should see here materials, and then you can click on edit. Then there is this silicon nitride. You can see, huh?
Nitrate or nitrate? It's nitrate.
It's nitride. It's okay. It doesn't matter. It doesn't matter because the value is anyway is not correct. You just see view/edit material, and we're gonna just basically put it. The value is 7 because it's measured for microwave domains. It's measured for 9.4 gigahertz. At 780 nanometer, this value is very close to 4, or refractive index is very close to 2. So put the permittivity to 4, and then click OK, and then again click OK, and then OK again. So now you should have waveguide made of silicon nitride, and then the substrate around it should be made of vacuum. Okay, clear. Just stop me if you cannot follow. Okay, so before making measurements, let's just review what we have here. So we have the boundary condition around this object. If you come to this, basically tree on the left, huh? So if you come to this tree on the left, you would see that you have this basically boundaries, excitation, etc., etc. And the first one, let's just check them again. So you have if you click on boundary condition, we put this, outer layer radiation boundary condition. Let's, yeah, okay. So you have this radiation boundary condition, and then you have 2 excitation ports, and then the idea is exactly, basically, we want to excite from one port, and then, yes?
What's the material for the cladding part supposed to be? Because I think it's vacuum.
It's vacuum, so it's a waveguide in the air.
Okay.
So refractive index should be 1. So the idea is like we want to launch from the wave from one port and then basically read off the other port. My time is finished. Because you understand? So I have just started.
What time did you start?
Like 5 minutes ago.
Why so late?
Yeah.
You got something from this morning?
Well, exactly. Okay, that's not. So then, so the one difference here between in ANSYS and COMSOL is that in COMSOL you had to think about the meshing in advance. So you had to mesh it yourself. Here is different logic. The logic here is the adaptive meshing. And what is that? So what is adaptive meshing? So it's program, like, I discuss a lot what is a good mesh, and you need to remesh everything. So what does this program? It starts with like a random mesh, and then based on the solutions, it actually refines the mesh. For example, it refines the mesh where you have more electric field, for example. So it meshes that area again and then calculates. And then remember, I told you several times you need to basically make the mesh finer and finer, see the results are different or not. The ANSYS program does it automatically for you. And we will see how together, like, how does it do it. So now we have this excitation. The only thing that you need to take care about the meshing, and then we are done for like setting up, is this surface approximation that we did together. And what is the reason for that? Because I told you before, magnifier. Okay, I told you before. So I come into this, surface approximation, and then clicked on surface deviation in a manual setting should be 10 nanometer. What is that? I mean, I told you this simulation softwares, they don't understand the curved surfaces. So they approximate these curved surfaces with bunch of straight surfaces. And this 10 nanometer basically tells you how much deviation you're letting the software to have from the curved surfaces. So if you break a curved surface into a bunch of straight ones, so how much deviation you can have? This is 10 nanometer. This is also good. So this we also set it up, and now we can put a setup. So what is it? If you double click on this, setup, you would see this window, which, well, magnifier. Why close it? Okay. So let me just magnify this again to see. So obviously, I think we need to shift the schedule by like half an hour at least, because we started really late and I'm covering what is in the morning. So you can sit down, like, instead of waiting, because you're just making me nervous giving this talk. Yeah.
Just looking for the chair, actually.
Yeah. Well, there are a bunch of things you need to know about this simulation. Well. So first of all, obviously it's a single frequency. I told you we are trying to simulate the equations of motion in frequency, phasor domain frequency. At this single frequency of 364 terahertz, which is really close to 780 if you calculate. So what is the number of pass? What is this delta? So I told you it refines the mesh, and then it calculates how much the error you get. And how does it calculate? It's in this S parameter. I mean, S parameter is a complicated parameter, but practically it just calculates the energy. It sort of relates to energy. So it calculates if the energy of the system changes if you refine the mesh. And then here you can set an error bar. Now it's 2%. So if the error bar is like less than 2%, it accepts it as a good mesh. And obviously we have maximum number of passes, which we put here 6. it means like it does maximum 6 iteration. I mean, you can put it more, but it takes just longer. So in the interest of time, actually, I just reduced this to 5 because remember, like more passes you have, the finer the mesh becomes, and then the longer the simulation will be. But let me just make a suggestion for those of you who will do simulations later. So normally what I do is I put the minimum number of passes to 3 to make sure at least it does 3. Even if it met this 2%, it's a good practice to do at least 3 iterations. And then minimum number of these convergence passes, I put it in 2. What is that? We will see it in a second. Is that so when you refine the mesh, you see this convergence plot, and sometimes this convergence plot oscillates. So it goes down and then it comes up, and so we want to give it like it goes down. You have 2 successful traces at least like this number of times, which we put 2. So we want to have at least 2 times, which is better than this error bar. Okay, with that, our setup is also concluded, and then we can run the geometry. So one good, basically, I close the magnifier again. So one good, suggestion here, if you come on here on the top, you see this, checkbox. Just click it. It will just kind of check you all the. It will just check all the basically properties of your setup, like 3D model, design, boundary condition, mesh, analysis, optimization. If you have radiation, these 2 we don't have. If all of them are checked, you can run this simulation. If you don't have some of them, like actually you don't put the boundary condition, you would see like alarm here, and obviously the simulation is you have a syntax error in simulation. So this is checked, so we are good to go for simulation. And to do the simulation, okay, let me just do again. So next to this, basically green checkbox, you have this, basically analyze all, and just press on it. And then it does some stuff. One of the good things about ANSYS is that we can see the results, updated as we go forward. It's not like COMSOL that we need to wait till the simulations are finished, and then we do the plotting. We can do it meanwhile it's doing the simulation. Every iteration that it does, we can see directly the results of this iteration. So here, actually, if you click on here like this, show the progress and the messages at the bottom here, so you would see. First of all, the first thing you need to do, maybe I again go to magnifier. You can track this like to see how the successful traces that this like iteration is going. Like if you want to plot it visually, you can go to this basically HFSS menu on the bottom, and then you go to results, and then go down all the way down, and you can see this thing which is solution data. So if you open that, a new window opens. Let me just go out of this magnifier. A new window actually appears, which contains all the information regarding convergence, and the second tab is actually the convergence matrix or convergence plot. Obviously, he has so in the left axis is the number of passes, and then in the y-axis is this error parameters we saw together, the S. So now it's at pass 1. Obviously, at pass 1 there is no error. It would start to make the errors from the pass 2. We will see. We keep this window open. Let's just minimize it. But since it has already finished the pass 1, we can start, basically observing some of the data that it actually tells us. So this boundary condition that we set is in a way that it actually basically calculates the modes of one port. It launch a wave on that mode and then let it propagate, and then see how much of it comes from that particular mode on the second port. So the first thing we can see, so first what it does, it just make an argand mode. So the first thing it has is the argand mode solver on the port 1 and 2 to see basically calculate the shapes of these modes. And you can see the results of it. If you go to your tree, you see ports and fields. At this point, it's already plotted. If you, for example, click on mode 1 and then double click on mode 1, and you can just zoom in. Okay, so you can see the electric field. Let me zoom in. I'm sorry. So you can see the electric field. This is the electric field distribution for mode TE01.
I have a question.
Yeah.
If I remember correctly, the ANSYS is not able to consider the bending, right?
No, it assumes a straight, infinitely straight waveguide.
Basically, this eigenmodel is not a curved respect.
No, it assumes like it's connected to a straight waveguide. So we are not coupling the WGMs. No.
But the case is actually, but the case is that you calculate the S matrix for one-to-one projection, right?
Yeah.
If your target model is not the same eigenmodel, and it's actually the S matrix doesn't give you the correct result.
Depends what I want to do. So what I want to do is not the question that normally you had in your research. So you were trying to see how much I come from this waveguide and how much it goes to the whispering gathering mode of this cavity. Here is not what I want to simulate. Imagine I have a straight waveguide connects to it, and then it's bended, another straight wave comes out, and I want to say how much it goes through. This is the first example of waveguide.
Then you have to kind of put another kind of